All right, good morning. This is 9-7, linear, quadratic, and exponential models. And go ahead and put these three tables in your graph. Let me get this up. There we go. These three tables on the bottom in your graph. The first one's linear, y equals mx plus b. And then we have quadratic, and we also have exponential. Okay, so what we want to do is we want to make sure we can tell the difference between linear, quadratic, and an exponential function. So what we're going to do is, for number one here, this does not go into your notes. We are just trying to match them up. So for letter A, I see I have a dot located forward 1, up 3, and then a dot located 0, 0. And if you compare them to the graphs here, the only one that starts that would be this one right here. And if you look at the pattern for this one, it makes a parabola, so that is a quadratic equation. Letter B, there's a dot at 0, 2, so compare these two graphs here. The one that looks like has a dot located at 0, 2 would be this one. So if we keep on going here, negative 1, 4, yep, this is definitely the one here. Now this one is going down with a curve, so it is exponential. And the last one, we have a dot located at negative 1, down 2, so this one definitely matches up. And this is a straight line, so this one here will be our linear equation. So just tell them the difference between quadratic. Same thing with this one, you plot the points and tell which model is most appropriate. Okay, so there's three parts here. I want to make sure we organize this correctly. What we want to do is be able to look at a table and not have to graph it and still be able to tell whether it's linear, quadratic, or exponential. One thing that has to happen for all three of these tables is if you look at the x column here, here, and here, notice how everything has to be consistent on the left-hand side. You see the hoop and the +1 for each table. So your x values have to be consistent. Now your y values, let me give this one here. This would go into your notes, this table on the left over here. And this is an example of linear. It's a linear equation because when you try to find your difference between your y's, they are consistent. So your common first differences on this one is +3. To get from 2 to 5, you have +3, and that goes the same thing with 5 to 8. If you notice that pattern, it is a linear model. The one beside it here is exponential. It's exponential if you have to multiply to find a common ratio. So how do you go from 0.25 to 0.5? Well, you do the opposite of times naturally. You take 0.5 divided by 0.25, and that'll give you a number of 2. And then if you do that for every single one, so let's say we take 2 divided by 1. 2 divided by 1, how do you go from 1 to 2? You have to times by 2. How do you go from 0.5 to 1? Take 1 divided by 0.5, you'll get a common difference, common ratio of times 2. And the last one is quadratic. It is quadratic if you check your first differences, which is this one right here, and you get nothing. And you've also checked your exponential by trying to find your common ratio, and that didn't work either. So then go to your next set of numbers. Well, how do you go from -2 to +2? You have to add 4. Now I want to check to make sure that's consistent with the next one. How do you go from 2 to 6? You add 4. So the first differences did match up, but your second differences, this row here, did match up. That's how you find out if it's quadratic. So these ones here go into your notes. Which type of function best models the data, use differences or ratios? So what I like to do first is just double check, make sure that your x's match up. So this always should increase by 1. And they all do. The next thing is I would check your common differences for your y values, meaning when you have to add or subtract to get to the next one. From 9 to 5, you would have to subtract 4. From 5 to 1, subtract 4. Now, if that's consistent with the whole, it is definitely a linear model. And that's the answer for this one, a linear model. One letter B here, just double check the x's to make sure those are all consistent. And they are. Okay, so if we would subtract this one here, we find that from here to here would be a negative 0.25. If we do this one here, we would get 0.75. And the next one, negative 1.25. Okay, so those don't match up, so it's definitely not linear. So the next thing we want to do is, since we have this set up already with our first differences, let's check our second differences. So how do we go from negative 0.25 to negative 0.75? We have to subtract 0.5. And then how do we go from negative 0.75 to negative 1.25? We'd have to also subtract negative 0.5. Now, since these match up, and I should be checking all along the way here, but they do match up, so that is an example of quadratic. All right, this one goes into your notes. And we're still doing the same thing. We're trying to find which model best fits what's going on with the table. If we do our differences for this one, what you'll get is from 12,575 to 11,065, you would have to subtract negative 1,510. And then from the next one you get 1,315, and the next one you get 12,300. Now this isn't working out, so it's definitely not linear. Let's check our second differences. Here you have to subtract 195, and then you have to subtract 85. Well, that's not working either, so it's not quadratic. So it's probably exponential, but we have to double check to make sure. When you check exponential, take your second number divided by your first number, so that way you know how to multiply from your first to your second. So your common ratio is 0.88 when you divide. Take 9,750 divided by 11,000, you come up with 0.88. And then we'll check one more. It looks like it's working out. 8,520 divided by 9,750. When you divide that out, you come up with 0.87. Now, I know it seems like it's different because we have a slightly different number, but it is exponential. The second part of this is writing the equation. When you write the equation, take your initial amount and set it up into this equation. Your initial amount is 12,575. Your R is your common ratio, which is 0.88. Raise it to the x power, and this is your equation. And that should be it. The other ones, you should be able to know how to write a linear equation and a quadratic equation based off of what we learned in the past.